Hi, I'm Amy. This is Liam. We worked in collaboration with Mo and Jim, who's our advisor, and we were presenting on new perspectives on flexibility and simple temporal planning. So to begin, I'll start with a brief example to show what kind of flexibility is useful for. So imagine a scenario where you have a group of rovers on Mars that have to act according to a particular schedule, and sending a schedule requires that to be sent from Earth, which takes somewhere around, say, 24 minutes. So we want to reschedule as little as possible. So essentially, we want a schedule that's flexible and allows for robustness to errors. So for example, if one rover were to complete an event late, we'd want the schedule to be flexible enough so that everyone else can continue to operate without having to completely reschedule. So the particular schedules we're looking at here in our research are simple temporal networks, or STNs, which essentially consist of a set of time points and a set of binary constraints between those time points. On the right, it just shows a graphical form where the points represent the time points, the edges represent the constraints, and the edges signify the passage of time between events. In addition, there's also a 0 time point, which just represents the absolute beginning of time that everything else is relative to. So now I'll go over a couple of previous flexibility metrics to show what other people have been looking at here. So to do this, I'll use a very simple example of an STN with two events, T1 and T2, where T1 and T2 both occur within the time interval 0 to 5, and T2 must occur after T1. So the naive metric simply takes the sum of the ranges of the constraint intervals for each event. So in this case, T1 and T2 both occur in the interval 0 to 5, so the total flexibility here is 10. So as you can see, the naive metric completely ignores the dependencies between events, and so this can be seen as a very significant limitation here. So the next two metrics attempt to take into account for dependency. The first is the Hunsberger metric, which adds to the naive metric the sum of the tightest constraints on each pair of events. So here we have one pair of events, T2 and T1. Their constraint has a size of 5, so the flexibility here becomes 15. So the next metric that attempts to account for dependencies is the Wilson metric, which decouples an STN into an interval schedule, which basically is an assignment of independent intervals to each event such that any assignment of times to those intervals is still a valid schedule. So in this case, we could assign the interval 0 to 2.5 to our first event and the interval 2.5 to 5 to the second event. And any assignment of times to these should result in T2 occurring after T1. And the Wilson metric takes the maximum interval schedule, basically, that maximizes the sum of the intervals to get flexibility. And so in this case, the maximum is 5, and we have a flexibility of 5. So in our research, we attempted to look at STNs and flexibility in a geometric way to see if we can get a more accurate or better metric of flexibility.
So yes, some of our key insights in this work come from the observation that the solution space for an STN is an n-dimensional polytope, where n is the number of events in the STN. So if we look at our example STN from before, where we have two events happening between 0 and 5, where T2 must happen after T1, we can graph these constraints. And the first constraint yields us these two boundary lines. The second constraint yields these two boundary lines, and the third yields two more, giving us a final solution space of this green triangle. Now, it's worth noting that since the naive metric doesn't take into account dependencies between events, it would consider the STN with this solution space to have the same flexibility as the STN with this solution space, even though this solution space is half as big. We can also think about the Wilson metric in a geometric fashion. In decoupling this STN, we would add the constraint that T1 must happen before time 2.5 and T2 must happen after time 2.5, and that would give us two more bounding lines, reducing our solution space to this square. Once again, there's something a bit unintuitive here, because the Wilson metric would consider the STN whose solution space was this square to have the same flexibility as the STN whose solution space is this entire triangle. So in an effort to prevent these sorts of unintuitive properties, we propose a set of 4 desiderata for flexibility metrics, which we hope will ensure that they behave in a more intuitive way. Now, in doing this, we make a few assumptions, and the main assumption here is that any event in the STN is equally likely to be perturbed in any direction and equally likely to be perturbed as any other event. Under that assumption, we think these are desirable qualities for a flexibility metric. If you had a different model of uncertainty in your STN, then you might want to rework or reconsider these properties. So the first of our desiderata is simplicity. And this captures the idea that if your STN has more events, that is adding complexity, it's adding ways to fail, and so it should be considered less flexible. So we say that a metric has simplicity if you have an STN, adding an event to that STN will not cause flexibility to increase. We also define a strong version of simplicity, and in this case, we add the qualification that the flexibility of a new STN that comes from adding an event should only be the same as the flexibility of the previous event if the new event is totally unconstrained, because that essentially will have no impact at all. Our second desideratum is density, and this captures the idea that busy schedules should be seen as less flexible. So if your, oh, that got terribly pixelated. If your class schedule looks like the example on your right, if one of those classes runs late, you are likely to be late to the next class. However, if it looks like the example on the left, one of those classes running late is unlikely to impact the other classes. To state this formally, we define a sequential STN as an STN that has n events which must occur in some predefined order and must occur within some fixed total interval. And we say that a metric has density if, as the number of events n approaches infinity, the flexibility approaches 0. Our third desideratum is sphericality, and this is the first of our geometrically inspired desiderata. It attempts to capture the idea that an STN is only as strong as its weakest link. And when we make the assumption that all events are equally vulnerable to perturbation, we can measure the strength of the weakest link by looking at the size of the largest inscribed sphere in the STN solution space, because the constraint on the size of that sphere is going to be the thinnest part of the solution space. So we say that if we have two STNs which have the same number of events and whose solution spaces have the same volume, the one with the larger inscribed sphere radius should be considered more flexible. The reason that we require them to have the same number of events is that we don't want to make this comparison across polytopes of different dimensionality, because that can become misleading. Our final desideratum is containment, and this captures the idea that, other things being equal, if you have more possible solutions, you should be considered more flexible. The way we state this is that if we have two STNs, again with the same number of events to avoid comparisons across dimensionality, and one of those STN's solution set is strictly contained within the other STN solution set, that first STN should be considered less flexible. We also define a weak version of containment, which changes that less than statement into a less than or equal to statement and says the contained STN should be considered at most as flexible as the containing STN. So, how do pre-existing metrics do with regard to these desiderata? Well, the Wilson metric does have containment, and the reason for that is that the solution space of the decoupling that the Wilson metric makes when calculating flexibility will be contained entirely within the solution space of the original STN. So in our example before, the decoupling has a solution space of this square, and it's contained within the triangle that is the solution space of the entire STN. As such, if your whole STN solution space is contained within some larger solution space, that larger solution space will also contain the solution space of your decoupling. And that means that it is going to contain a decoupling at least that good. So it will have at least that much flexibility. So the Wilson metric does satisfy containment, although it only satisfies it weakly because it would consider the STN whose solution space is this square to be just as flexible as the STN whose solution space is this entire triangle. Moving on to other desiderata, the Wilson metric does not satisfy simplicity, and the reason for that is that if you were to add a new independent event to an STN, that won't change how the Wilson metric decouples the other events. And so when you sum the intervals in the decoupling, that new events interval will be added in, giving you a larger total than previously, so flexibility will increase rather than decreasing as simplicity would require. The Wilson metric does not have density either, and the reason for that is that when you have your sequential STN, as the number of events in that sequence increases, while the Wilson metric will decrease the interval on which each individual event can happen, but the sum of those intervals will always be the same. It will be the size of the fixed interval on which the entire STN needs to be executed. And as such, as the number of events approaches infinity, flexibility will remain constant rather than tending towards zero as density would require. Finally, the Wilson metric does not have sphericality either, and we can look to a counterexample to see this. If we have an STN with two events, one of which needs to happen between 0 and 1, and the other of which needs to happen between 0 and 100, the Wilson metric will assign that a flexibility of 101 because it will just add those intervals since they are already decoupled. And the inscribed sphere will have a radius of 0.5 because it's a long, skinny rectangle with width 1, or the solution space is. We can compare that to an STN where we have two events that need to happen between 0 and 10. The solution space of this has the same volume as the previous one. The Wilson metric would assign it a flexibility of 20, once again adding the intervals because it's already decoupled. And the inscribed sphere would have a radius of 5, which is greater than 0.5 in the previous example. So we see here that the former STN would be considered more flexible by the Wilson metric, even though it has a much smaller inscribed sphere. I won't go into this level of detail with the other previous flexibility metrics, but in general, they perform about the same way that the Wilson metric does, and generally for very similar reasons. The naive metric has the same properties as the Wilson metric, and the Hunsberger metric differs only in that it strongly satisfies containment rather than weakly. So now I will hand it back to Amy to talk about some new flexibility metrics that we propose.
So based on our geometric view of STNs, we came up with a couple of new flexibility metrics. So the first one is the ratio of volume to surface area of a polytope. So the idea of this came out of the fact that, that volume is the entire solution space of an STN, and the surface area measures something like the number of ways a solution might fall out of the STN, or like if an error occurred, the likelihood that it would fall out. So that is intuitively what the ratio of volume to surface area would measure. It's not really feasible to compute because volume and surface area both take exponential time for STNs, and so this isn't entirely feasible, but we thought it had some interesting properties that we wanted to look at. So running through the desiderata for the volume to surface area metric, it does satisfy simplicity and density with some math that we have more of in our paper. However, we were actually surprised that it didn't satisfy sphericality and containment, and so I'll run through a couple of counterexamples for those. So a counterexample for sphericality, if we consider two STNs, one of which is a rectangle and the other of one is a parallelogram, based on sphericality, the parallelogram should be more flexible. However, the volume to surface area ratio of the rectangle is actually a little bit higher, and this is sort of because of the sharp corners of the parallelogram, so it's sort of less round. A schedule that would be in one of those corners would be more likely to error, and that's sort of what volume to surface area captures. We see the same thing in this other counterexample that shows that it doesn't satisfy containment. So in this case, we have two STNs, one of which is a triangle, and the other one is the STN when you chop the top of the triangle off and get this trapezoid shape. So by containment, the triangle should have greater flexibility since it contains the other STN. However, the trapezoid actually has a higher volume to surface area ratio, And again, if you were to imagine that there was a schedule in the very tip of the triangle, any small error would likely cause that to fail. And so that is what we see the ratio of volume to surface area really capturing. The next metric we had was the sphere metric, which was inspired by our sphericality desiderata. So this metric is the nth root of the volume of the inscribed sphere, which is sort of a very roundabout way of saying almost the same thing as the radius of the inscribed sphere, but by properties of the nth root and the volume, it happens to satisfy our second desiderata, which is density. So the radius of the inscribed sphere, again, just captures the idea of the thinnest interval of flexibility in an STN. And the sphere metric can be computed using linear programming in low-order polynomial time. So this can actually be used in actual applications. So we'll run through the desiderata for this metric. For simplicity, it satisfies weakly. Since adding an event will not affect any of the existing events, so geometrically, the flexibility should not be able to increase when we add a new event and add new dimensions. For density, it satisfies because the volume of a sequential STN we computed to be k to the n over n factorial, which does go to 0 as n goes to infinity. Trivially, it satisfies sphericality, and it satisfies containment weakly because if you have an STN that contains another STN, the inscribed sphere will be at least as large. So here is just a summary of all of the previous and also our new flexibility metrics. As you can see, the sphere metric weakly, at least weakly, satisfies all of them and also can be run in efficiently. So we thought this was pretty exciting. So that's it. So our future work, we think it would be interesting to apply these ideas to probabilistic STNs or STNs with uncertainty. We also think it would be interesting to combine metrics to try to get strong satisfaction of all desiderata, or apply these metrics to specific types of scheduling problems. That's it for our presentation. We'll open it up for questions.
Do you have any questions for the speaker?
Wonderful, thank you. Very interesting presentation, thank you. So within scheduling, often these measures of flexibility are used for variable and value ordering in deciding temporal resolvers of resource conflicts. And for example, the Huntsberger metric can be used to predict most constrained and least constraining, most constrained variable and least constraining value in the scheduling problem. Have you thought of whether this quality applies also to your metrics, and do you think you can use these in doing these variable and value ordering decisions?
That wasn't an application that we personally were aware of, but it sounds like a really interesting direction for future work.
Okay. All right. Who's next?
Any other questions? Let me back to speaker.